until the end. It should be muted, yeah. My name is Evgeny, and I will tell you just few words about administration and organization. So we have lectures. The lectures, all of them will be online in this Zoom conference. I hope you will need use only one Zoom link for all the conference. So do not forget it, and I'm sure Pavel will remind you every time where will be the next lecture and so on. During these lectures, we will mute everyone except of our speaker, of course. So if you want to ask a question or make a small comment, please use chat. So you can write your question in a chat, and then one of us, of moderators or even speaker, will read your question and maybe even give an answer on it. Or you can just use your space button to unmute yourself, and then you can ask this question. Okay, so it's very good, I think, in my opinion, it's very good if you don't understand something, maybe not so much, but anyway, that you will ask a question or make a comment, that you will make our school more alive. So it's always good. So please ask these questions. Also, except of lectures, we have seminars. The next seminar will be on Friday. The main idea of seminars is that students make seminars for students to better understand lectures. Of course, everyone is welcome, but anyway, this is like students' work and they will do something interesting for them. And only the last administration organization moment. At the end of the lecture, we ask you to turn on your video so that we can see how you looks like, that you are not only this black space board here with white title, that we will see how you alive after the lecture. So please do not sleep. And at the end, we will ask you to turn on your video, prepare yourself, make everything you want. So that's all about administration questions. And now I ask Sergey, could you please introduce our speaker? And Sergey said that he is muted, but you can use space button to unmute yourself.
Ah, myself. Okay. Okay. So I thought, okay, thank you. So thank you for inviting me to say a few words about Ganesh. So the Ayalvadi Ganesh. I never so Ganesh. I used to say Ganesh because it's better for him. He told me that it's better to call him Ganesh and so on and so on. We know each other for about 20 years. Ganesh did his PhD at Cornell. After moving from India at Cornell University with Professor Venkat Anantaram, and then he moved to Bristol to the BRIMS, yeah, Ganesh. It was
yeah. BRIMS.
It's very interesting. It was very interesting research institute which existed for about 3 or 4 years only. Then it closed, and then there were many people. It was a very nice time. There were many people around, like Neil O'Connell, like James Martin, and many other people who were around and. Who became full professors around the world now in many countries. Then Ganesh joined Microsoft Cambridge, and he worked there for almost about 10 years, maybe. And then he moved to Bristol, where he is now. And Bristol, University of Bristol is one of the most known universities because it was the famous John Kidman is still there. He is a colleague of Ganesh, and Ganesh can see him on research seminars and students in Novosibirsk know the celebrated Kidman subadditive ergodic theorem or theory, whatever, and so on. So Kidman is yes, and so yes, I think Ganesh works with there are Bali Todd and many other people, and there is a very nice and creative research atmosphere at the University of Bristol. Ganesh is a well-known specialist in many areas of probability theory, starting from, I would mention first the book by him, Neil O'Connell, and Demon Vishik on big Qs, which essentially is a book about the large deviation theory. So Ganesh made a significant contribution to this area in general probability theory, but also in many applied probability areas, including queuing theory, communication networks, distributed algorithms, epidemics, what else? Peer-to-peer networks and so on and so on. So he's and he just I can see I see that his paper, last paper, just appears at the Annals of Applied Probability, and Ganesh plays plays a very important role in the applied probability community. It's a big applied probability community in the world, and in particular, he serves as a member of editorial board for the Annals of Applied Probability for queuing systems, and at many other in many places and so on. So we meet each other for regularly, at least a year, every year, or even frequently. And I believe that Ganesh will give a very good lecture course, which is very, very intriguing, I would say, title to me. First of all, Rumour. Rumour means something, you know, in Russia, it's like sluhi or even spletny. Formally, it's, how to say, yeah, it's
we didn't find translation of this word as well.
No. Rumour is okay. Rumour is your information which was unverified, unjustified information. It's rumour. Consensus, it means that yes, I would say the following. Ganesh will correct me. I would say that many people spread a rumor, and now several of them decided to make a consensus to have a joint rumor, which looks more comfortable. So I think it's completely wrong, but I think Ganesh will correct me. So it's a unified a humor or common humor which comes from all sides. I would say consensus like this. And then finally they start to spread this rumor around the world, and it creates the epidemics. Ganesh, is correct?
Yeah, fair enough. It's
Okay, so I stop, and yes, I forward to this. Yes, I stop for now, and I see you at the end of your lecture. Okay, thank you.
Thank you, Sergey. Thank you for the introduction, and thanks to the organizers for the invitation. I'm sorry that I can't be in Novosibirsk in person this time. Hopefully there'll be a chance to do so next year. But yeah, so these lectures will happen online. And it's also the first time for me doing a course like this online. So hopefully it goes smoothly. And I just wanted to repeat what Evgeny said earlier. So please do feel free to interrupt with questions if you have any questions. Yes, so I'm going to start sharing my screen now. Let me know if there's any problems seeing it.
Okay. Yeah, we can see it.
Okay, perfect. Okay, so this course will be about a few topics related to stochastic processes on networks. The motivation for studying many of these comes mainly from computer science and my own work. So the processes we study form parts of many distributed algorithms in computer science, but they also have other applications in social networks and biological networks. For instance, in how information spreads in social networks, information about, say, jobs, for example. How do people search for jobs? How do technologies disseminate? These behave in some ways like the rumor spreading processes we look at, and sometimes there may be competition between different technologies, and then consensus may correspond to one of these winning the competition and so on. And also it's not only humans, but many animals do similar things. So they have For example, bees have to decide which of different places to go to search for food. And then the scouts go out and come back and perform some kind of dance on the surface of the beehive. And this communicates information, and the whole hive goes in this direction. So insects are also involved in these processes of reaching consensus and deciding where to go to search for food or nests or so on. So there are many applications, but mainly we look at simplified mathematical models of these processes, and that's what this course is going to be about. So the first lecture will be about two related processes of rumor spreading and first passage percolation. But before introducing these, I just want to start with some preliminaries, which are probably familiar to all of you, but let's go over them quickly just to confirm. And if there are any questions, of course, stop me. The Poisson process is going to play a very important role in everything we do. All the processes we look at will be built on top of Poisson processes. So let's review what that is. Firstly, time will be continuous for most of this course. So time will be indexed by the real line or the positive real line. And the counting process is a stochastic process which takes values in the non-negative integers. You count the number of things that happen up to some time t. Without loss of generality, let's say it starts at 0. At time 0, no events have occurred, and up to time t, some random number of events have occurred. And so this is not decreasing because you just count the total number of events. And such a counting process is said to be a Poisson process if there are many different ways, equivalent ways of defining the Poisson process. And here are two of them. The first is the process has independent increments. And if you count the number of increments between time s and time t, then this random variable is a Poisson random variable with mean lambda times t minus s. So the size of the interval times some positive parameter lambda. Or equivalently, if you look at the times between successive increments of this process, successive jumps of the process, then these times are IID, independent and identically distributed, and they are exponential random variables with parameter lambda. And so the process has this parameter lambda in its description, and this is called the rate or the intensity of the process. And you can see more easily from the second description that the increments happen one at a time. You don't have multiple simultaneous jumps of this process. Okay. So the exponential random variable doesn't have an atom at 0, so you don't have 2 or more jumps happening simultaneously. So that's the Poisson process. It's a process where jumps happen one after the other, and the times between jumps are exponential random variables. And let me also remind you the memoryless property of the exponential. So if we know that this random variable is bigger than x for some fixed x, and we want to know how big it is, then the future is independent of the past. So the probability that it's bigger than x plus y, conditional on being bigger than x, is the same as the probability it's bigger than y. Okay. So you can think, okay, concretely of waiting at a bus stop. So if you have been, if the buses come according to a Poisson process with a mean of 30 minutes and you've already been waiting 20 minutes, you don't know how much longer you have to wait. You still have to wait another 30 minutes for the bus. Okay, so that's the Poisson process. And there are a few properties of the Poisson process we'll use repeatedly, so just let's review these. The first is the rescaling of time. So if you have a Poisson process with intensity lambda and you speed up time by some factor beta, then the rescale process is again a Poisson process with intensity beta times lambda. So the units in which you measure time don't matter, they just change the rates of the process accordingly. Okay, and then there's the superposition property. If you take two independent Poisson processes with intensities lambda 1 and lambda 2, and you take the superposition of these, you count all the events of both these processes, then the result is also a Poisson process with intensity, which is the sum of lambda 1 and lambda 2. And finally, the splittings. So if you have a Poisson process with intensity lambda, and you have a sequence of coin tosses, so you have a coin which comes up heads with probability p, and then you split this process by looking at each of the points of the process, toss a coin at that time. If it comes up heads, put it in the N1 process. If it comes up tails, put it in N2. Then the split gives you two independent Poisson processes with rates lambda times p and lambda times 1 minus p. And hopefully you were already familiar with all these things, but I'm just reminding you of these things. Okay, so these are things we will repeatedly do with Poisson processes throughout the course. So that's the preview of Poisson processes. And similarly, let's just do a very quick preliminaries over networks or graphs. And I'll use these terms interchangeably to mean the same thing. So a graph or network consists of a set of vertices or nodes V and a set of edges E. And an edge is just a pair of vertices, an ordered pair of vertices. So we'll call the edge undirected if the order of the vertices doesn't matter. So if UV or VU mean the same, refer to the same edge. And then we'll call the whole graph directed or undirected if all its edges are directed or undirected. Mostly we are only going to be studying finite graphs in this course, so the number of vertices will be finite. Very occasionally we'll talk about infinite graphs as well. Some definitions. So if we have a sequence of distinct vertices, V1 through Vn, and for every succeeding pair of vertices, either there's an edge from Vi to Vi plus 1, or if there's an edge in the other direction, we'll call the sequence a path. So we don't care about the direction and the path, we just care that there's an edge in either direction, and then we'll call it a path. If the directions, if the edges go in the correct direction, we'll call it a directed path, but otherwise we'll just call it a path. And then if you have a path and there's also an edge from the last vertex to the first vertex or the other way around, V1 or V1 Vn is an edge, then the path going back to V1 is called a cycle. Okay, so these are just common terminology. And remember that the vertices are distinct in the path. If the vertices are not distinct, we'll call it a walk. Okay. Okay, so, and just one other convention. So if you just go V1, V2 and back to V1, we don't call that a cycle. So a cycle, you must go at least, there should be at least 3 edges on the cycle to call it a cycle. A few more terms. We'll call a graph connected if between every pair of vertices there's a path, ignoring directions on the edges. So it's possible to go from any vertex to any other vertex, possibly traversing edges in the wrong direction. And the graph is complete if the edge set consists of every pair of edges. So if it's directed, that means it's present in both directions. If it's undirected, it's present ignoring directions. Then it's called complete. And a complete subgraph of a given graph will be called a clique if you have a set of vertices within a graph such that within those vertices every pair of edges is present. Okay, and then an undirected graph is called a tree if it is connected and if it has no cycles. Okay, so those were all the preliminaries. I guess there are no questions about those. No? Okay. So then we move on to the models we are going to study today, the two models. So first is the spread of rumors. And we'll start looking at this on the complete graph, which on n nodes, which we denote K sub n. Okay, so we have a population of n nodes. And to start with, just a single node U knows some item of information, which we call a rumor. And this is going to spread through the network in the following way. Whenever some node V learns the rumor, or maybe even before it knows the rumor, so every node V is communicating according to a Poisson process. So there's a Poisson clock sitting at each node V, and every time this clock rings, the node V is going to communicate with somebody. So whenever it rings, V is going to pick a node W uniformly at random from the vertex set, from all n vertices. And okay, just for convenience, we'll assume it can also pick itself. And if V picks W, then V is going to talk to W. And if by this time V already knows the rumor, then it will pass on the rumor to W. If V hasn't heard the rumor by this time, then nothing happens. The communication is empty. Okay. And then the Poisson processes at all the nodes are independent, mutually independent, and who they choose at each time is also independent of everything else. And the question we are interested in is how long does it take until this rumor has spread to everybody in the network? So what's the first time t such that all n nodes know the rumor? Okay, so that's the first model, and I hope that's completely clear.
I think yes, but I can just try to repeat what you said, that I understand everything fine. So you have, let's say, n people, and only one of them knows something, rumor. Yeah? Each person has its own stochastic process, Poisson process, that mutually independent to each other persons. And so each person wait until the first exponential random variable. After exponential random variable, it chooses uniformly between everybody and say something if this person knows something. So this means at first moment we looked only on U, yeah, the single node using, and we wait exponential time until after this time, this person will tell someone uniformly, yeah, this rumor. It can also tell to itself, then nothing happens, yeah. And then it continue. And we are interested in the time when all nodes, all people will know something, this rumor. Am I right?
Perfect, yeah.
Thanks.
Okay, thank you. Okay, so that's the rumor spreading model. And there's a related model. In fact, we'll show it's the same model, and it's called first passage percolation. And this is not, so the rumor spreading was something happening over time. This is a static model. There is no time here. But what we have is a complete undirected graph on n nodes. And now we put weights on the edges. So each edge is assigned a weight or a length, which is a random variable, and it has an exponential distribution with mean 1. And let's call these weights W, X, Y. And now we fix one node U, and we want to know about shortest paths from U to all other nodes. Okay, and that's called first passage percolation. Last passage percolation is the biggest weight path, and first passage is the smallest weight path. So we look at the minimum overall paths between U and V of the sum of the lengths along those edges, Vi through Vi plus 1. Okay, so that is the distance from U to V. The distance is the length of the shortest, total length of the shortest path. And this doesn't have to be obviously the path consisting of a single edge. It's a complete graph. You can go from U to V in one hop, but the shortest path may involve going through many hops. Okay, so we want to know what this random variable duv looks like, and also the random variable du, which is the maximum of the distance from U to all other vertices in the network. So how far is the furthest vertex away from U? So this is another question we are interested in. And this problem is called first passage percolation. You may already see this, but the claim we are going to make is that these two models are essentially the same thing. Okay, so the random variables Tn and du are the same in distribution up to a scaling factor of n. Okay, Tn is n times du. And why is this? So let me explain that. Okay, so we can re-describe the Rumour spreading I described by putting a Poisson process at each vertex. And when this clock rings after this exponential random variable, we choose who to talk to. Instead, I could have described it by putting all the clocks on the edges, and that's the description we see now. So we are going to have independent Poisson processes on each of the edges. So NVW is the Poisson process on the edge VW, but the rate of this is going to be 1 over n instead of 1. And every time the clock on this edge rings, these are now directed edges. So whenever the clock on the edge rings, if V knows the Rumour, it'll tell the Rumour to W. If it doesn't know the Rumour, nothing happens. If W already has heard the Rumour, again, it's communicated, but nothing changes. And this edge, putting the clocks on the edges is equivalent to putting the clocks on the nodes because of the property of the Poisson process we saw that Bernoulli splittings give Poisson processes. Because what happens when you put the clock on the node and then you decide who to talk to at random, you can look at, you can first realize that sequence of coin tosses, which decides who to talk to, and split the Poisson clock on the vertex according to who you choose to talk to. And that's a Bernoulli splitting. And so that gives independent Poisson processes on each of the edges, and they have rate 1 over n. Okay. So rate 1 over n means an exponential random variable with a mean of n on the edges in this model. Whereas in the first passage percolation model, we have exponential random variables, lengths on the edges with a mean of 1. But except for this rescaling by a factor of n, they are both exponential random variables, so it's basically the same model. You can think of the length of an edge as the first time after a node. So when a node V hears a Rumour, it's going to look at the length of the edge, and after that time, it will talk to node W. Okay, so these two models are basically the same. Instead of putting the Poisson process at the beginning, you can just wait till the node V learns the Rumour and then sample the exponential and then say this is the time at which it will talk to W. And so the equivalence depends very much on the memoryless property of the exponential distribution. It doesn't matter whether you started the clock at time 0 or you started the clock at the time that we learned the Rumour. The next time it talks to W has the same distribution in either of these models. Okay, and so the difference in the Rumour spreading model is it looks like there is an infinite sequence of exponential random variables on the edges, but if you're looking at how long it takes to spread, it's only the first time you sample that exponential that matters. The second time you talk to W already knows the Rumour. So these two models are the same. Okay. It's fairly easy, but again, let me check to make sure that everybody's understood that these two models are exactly the same up to time scaling.
I will ask directly. Pasha, what do you think? Everything is fine?
Yeah, I think yes. Everything is fine, yeah.
Okay. Okay, good. So now we are ready to look at calculating these random variables. So let's analyze the time it takes for the Rumour to spread. Okay, so let's define T sub k to be the first time that k nodes know the Rumour. At least k and exactly k is going to be the same. Two nodes won't ever simultaneously learn the Rumour. So we started with one node knowing the Rumour, so T1 is 0, and we want to find out what is Tn, the time that all nodes know the Rumour. And we'll calculate this by looking at the times, the increment times, Tk plus 1 minus Tk. So at time Tk, there are exactly k nodes which know the Rumour, and there are n minus k nodes which don't know the Rumour. And it's the complete graph, so there's an edge between every pair of nodes. So there are k times n minus k edges going from informed to uninformed nodes. Okay. And only communications along these edges matter. So if an informed node talks to another node that already knows the Rumour, it's wasted. No information passes there. So we only have to look at this k times n minus k edges. Each of these has an independent Poisson clock running at rate 1 over n. And the first time that one more node learns the Rumour is when one of these many clocks rings. And so by the superposition of independent Poisson processes, the rate at which some clock rings is the sum of these rates. So it's k times n minus k over n. Okay. And so the time until one of these clock rings is exponential with this parameter. So the time for one more node to learn the Rumour is exponential with parameter k times n minus k over n. Very straightforward.
So this difference is the time period where when exactly k nodes know the Rumour, yeah?
So at time tk, exactly k nodes know the Rumour, and at time tk plus 1, exactly k plus 1 nodes know. So this is the time it takes until exactly one new node learns the Rumour. It has to learn from this set of k nodes. There are n minus k nodes waiting to learn, so there are this many edges. And 1 over n is the rate of communication along each edge. So this is the total rate of communication between nodes who know the Rumour and nodes who don't know the Rumour. Yeah. Was there another question?
Yeah, everything is fine. Thank you.
Okay. Okay. So let's first calculate the mean of the Rumour spreading time Tn. So Tn is we can write as a telescoping sum in this way. T1 is 0, and so by linearity of, okay, and first let's calculate the expectation of tk plus 1 minus tk. It's exponential, so the mean is the reciprocal of the exponential. We can expand it in partial fractions, and this is what you get. So it's 1 over k plus 1 over n minus k, and then by linearity of expectation, we add up all these things. And we get the sum of 1 over k. I guess the sum should go up to n minus 1. Sorry, that's a slight mistake. 1 over k plus 1 over n minus k. And these two sums are counting up and counting down from 1 to n. So it's 2 times the same sum. And you recognize that this is the harmonic series. So it's asymptotic to log n. So the expected time until all n nodes learn the Rumour is 2 times log n, asymptotic to 2 times log n. Okay, so this is a very easy computation, and there's just one comment I want to make about this: the scaling of this time with the parameter n. We are typically going to be interested in all these cases in asymptotics in most of the course. What happens as n goes to infinity? So what happens on large networks? And what you can see here is that Rumours spread very quickly. So in a network of size n, it only takes time log n for everybody to hear Rumours. And okay, so yeah, so it's a very spreading Rumours is a very effective way of communication, as maybe we know from social networks. It's also very useful for algorithms in computer science if you want to spread information using highly distributed algorithms, because this is a very quick way of spreading the information.
But may I ask like a question? If you have instead of 1 Rumours, who knows Rumour at 0 time, yeah? If you will have 2, then the answer will be very similar. It will be also 2 log n, just minus 1. Yeah, am I right?
Good question. So I will provide some remarks on this later. This problem has been studied of multiple Rumours as well. There are good bounds known on that. And yes, for k Rumours, the bound is okay. I don't remember the bounds, but yeah, it's not. It also is essentially like 2 log n. Indeed, it doesn't grow too fast with the number of Rumours.
Okay, yeah, thanks.
Yeah, let's see, how are we doing on time? Okay, so let's go a bit more. So that's the mean time for the Rumour to spread. And we can look at more refined asymptotics. We can calculate the variance in the same way. We can first start with the variance of tk plus 1 minus tk. It's an exponential random variable, so we know the variance of that. It's 1 over the square of the parameter. So this is the variance. And also from the construction, these random variables for different k are mutually independent. So we can calculate the variance of the sum, Tn, by summing up the variances. And if you do the calculations, you get the sum of 1 over k squared from 1 to n. The sum from 1 to infinity of this is pi squared over 6. And then again, there's the sum in the opposite direction. So we get pi squared over 3. And then there are some other terms which are vanishing.
Ganesh, I'm sorry. We have a question in chat. Sergey asks, Ganesh, assume you replace Poisson by renewal processes. What are the conditions for the asymptotics for such asymptotics expectation of Tn is equivalent to 2 log n to hold?
Good question. I'm going to come to this also in remarks in a short while, so I will take that a bit later.
Thank you.
Okay, so that's the variance. Okay, and just in case you are not familiar with big O and little o notation, I've provided definitions of those below. Okay, so the mean scales like log n, so it grows slowly with n. The variance doesn't even grow, it remains bounded. What we can do is we can, so if we look at Tn rescaled by 2 log n, the mean converges to 1, the variance to 0. And then we can use Chebyshev's inequality, which says that for any random variable, the probability it deviates from its mean by more than c is bounded by the variance over c squared. And if we do the calculations, that says the probability that Tn over 2 log n deviates from its mean by more than any epsilon tends to 0. And so the sequence of random variables converges to 1 in probability. So this is our first refined statement about the sequence of random variables. Not only do the means converge, the random variables themselves converge in probability. We can look at even finer scales and ask about fluctuations. So Tn has mean 2 log n. If you subtract off the mean, the variance is of order 1. This gives some hope to conjecture that maybe these centered random variables themselves, with no further scaling, converge in distribution to something. And is that true? And it turns out that that is true, that these centered random variables converge in distribution to the sum of 2 independent Gumbel random variables. Okay, so this is an interesting result, and I'm going to leave it as one of the exercises in this course. I'll give lots of hints, and you are all going to prove this for yourselves, that this is true. Okay, so that's the end of the first part. So I'm going to now make several remarks about the analysis. So the analysis relied very heavily on the memoryless property of the exponential, and because of that, it was very, very easy. So really, we should assume exponential, Poisson, etc., and analyze it this way. But indeed, as Sergey asked, we want to know, not just for exponentials, but for other processes, what it looks like. So maybe it's easier now to talk of the first passage percolation instead of putting edge weights which are exponential. What if we take some other distribution and put IID edge weights, let's say uniform between 0 and 1. So it turns out that the results are not sensitive to the edge weight distribution. You get the same answer for any distribution, but what it depends on, it doesn't depend on the mean, it depends on the density near 0. So where are we? So if the edge weights are IID, then all that matters is the density. For the exponential 1, the density is 1 at the origin. For the uniform 0, 1, it's 1 at the origin. So whatever you pick, so long as the density is not non-zero at the origin, you get the same thing. If the density is half, you rescale your exponential 2 has density half, or exponential half, one of those. So you rescale your exponential to make it the same density at the origin, and then you get exactly the same result for how long, for the distances in the first passage percolation, or for the time to spread the Rumour in the Rumour spreading model. And the intuition is here. Every time a vertex has n, let's again think of first passage percolation. A vertex has n choices of edges. And it's only the smallest few of these that are going to matter. There are NIID weights, but only log n of the edges will play a role in determining shortest paths in the graph, or some constant times log n. The heavier edges will completely disappear, will not be present in any of the shortest paths. Okay. And so if you're looking at n independent random variables and the first n smallest order statistics, then these only depend on the density very close to zero. So the density at near the origin is all that matters in determining all these. Okay. So it's
sorry.
Yeah.
We have a question from Sergey, and if the density in the origin is infinity, what can we do?
Good question. I don't know. What if it's infinity, or what if it's zero? I think then the Rumour spread is much faster, but these methods don't work. I believe Remco van der Hofstad and Shankar Pamidi have looked at some problems like that, but I don't know the answer to that question.
Okay, and if the edge weights are discrete random variables, can we say something about in this case?
Okay, yes. So the special case where the edge weights are geometric, which corresponds to the discrete time Rumour spreading model, where the time you talk after one time step, picking a neighbor vertex uniformly at random. That model was studied first by Fries and Grimet, and then more refined results were obtained by Boris Bittel. And there the scaling factor is again log n for the Rumour to spread. But the constant is different. It's not 2. So there the Rumour spreading time is so I should explain that when I say log n, I always mean the natural logarithm of n. But in the work of Fries and Grimet, what they got was it's the natural log of n plus log of n to base 2. So that's the Rumour spreading time. So it's a different constant in front of the log n. And so you would get the same thing for discrete random variables, but the logarithmic in n scaling is very robust. It's only the constant that changes with the models, but the log n scaling is very robust, except indeed if you have density infinity or density 0, that can change things.
Okay, thank you.
Okay. Okay. Yeah, so that was the first set of remarks, a bit more. Yes, so I already mentioned this about convergence and distribution of Tn after centering, and okay, and we can also study large deviations if you're interested. So the probability that Tn fluctuates, so it should typically look like 2 log n, but you can ask what's the probability it's bigger than some other constant times log n, so maybe bigger than 3 log n. Those probabilities decay exponentially in log n, polynomially in n, and you can get the rate of decay for that as well. And finally, the first passage percolation context, we looked at the shortest path problem for first passage percolation, but you can look at other combinatorial optimization problems in this setting by putting IID edge weights, and a lot of these have been studied. So what we looked at, shortest path, is also called broadcast tree, but you can also study minimum spanning trees and Steiner trees and traveling salesman problem and so on. And this is called the stochastic mean field model of distance, and these have all been studied. And here are several references about some of these problems. So the talk I've taken very much adapted from Svante Jansson's paper. So this is the most elementary result, and the paper is what we have covered in the talk. And there are more results in this paper. And these are several more of these combinatorial optimization problems I mentioned. Okay. So now is maybe a good time to take a break. And after the break, we'll talk about two things. So one is so I talked about the time for the rumor to spread on the complete graph. We'll also look at the hop count for the rumor spreading. How many hops does the rumor pass through before reaching everyone on the complete graph? And then we'll move on to general graphs and say a bit about that. Okay, so should we take a 10-minute break? Is that good?
Yeah, I think it's good. Thanks for the first part. So 10 minutes break, this means at 5:05.
Mm-hmm.
Yeah, it will be already 9. So 10 or 15. Let's make 14 minutes break and start at 5:10.
Okay.
Okay, 11:10 in English time. Yeah, American. Okay, 14 minutes break. See you.
See you. Know how many steps the rumor goes through before it reaches some specific node or before it reaches all nodes. So how many people were on the path between whoever started the rumor and me by the time it got to me. That's what we are looking at. Not just how long it took, but what the path, what's the graph distance along the path. Okay. And so this is related to the depth of, so if you look at which nodes are informed up to some time, it starts with a single node and it grows like a tree. So we are interested in the depth of this tree. So this is called the broadcast tree, or in the first passage percolation model, if you look at all the shortest paths, then the union forms a tree. That's the tree we are looking at. Okay. Okay, maybe I'll first show the picture and come back to this. So we start with a single node knowing the rumor, and then it informs some other node, maybe this one, and then it informs some other node. Meanwhile, this one informs this node, etc. And then there may also be edges from some node which is informed to some other node, but we don't care about those. We only keep track of where you first heard the rumor from. And so that gives you a tree, and it grows every time somebody else hears the rumor. And now you want to ask, so where did this person hear the rumor from? And maybe it's this, etc. So we want to keep track of this growing tree. Okay. So we'll denote by this curly T sub k, the shortest path tree, when it contains k nodes, including the origin itself. So at time, so T1, we start with just the source of the rumor. And we want to ask, given a tree Tk, what does Tk plus 1 look like? So which node is added and who is it added to? So here, so if the blue tree is the set of nodes which already knows the rumor, then what you have is potentially edges from these blue nodes to every other node in the complete graph. And there are independent exponentials along each of these edges, all with the same rate. So whichever of these rings first is going to be added. And by symmetry, it's clear that then you are uniformly picking one of the other nodes to add. And it's also going to be joined to one of the existing nodes picked uniformly at random. And that's all I want to get across. I hope that's clear. The tree grows by adding vertices one at a time. And it's added to one of the, so the edge from that new vertex goes to one of the existing vertices chosen uniformly at random. Okay. And a tree constructed in this way is called a random recursive tree. So the shortest path tree in first passage percolation is exactly a random recursive tree. So that's what I want to say. And I think I said that in lots of words here, but hopefully the picture is completely clear. So start with a single vertex, keep adding vertices, joining it to one existing vertex, so it remains a tree, and you always pick uniformly which vertex you add it to. Okay, and now we want to analyze the depth either of the tree as a whole. So here the depth of the tree is 2, or we may pick a vertex uniformly at random in the tree and ask what's the depth of that randomly chosen vertex. So if you happen to pick this vertex, its depth is 1. Okay, so let's denote by x sub k the depth of a uniformly chosen node in the random tree tk obtained after adding k nodes. To start with, there's just the root, so its depth is 0. And then we want to know how these two are related. So you have the tree tk, you add one more node, and you pick a node uniformly at random from tk plus 1. So with probability k over k plus 1, it was already in tk and was chosen uniformly from that. So its depth is distributed like xk. Or with probability 1 over k plus 1, it is the new node that you added. But the new node you added is equally likely to be added to any existing node. So it was added to an existing node at depth k with one more edge, so its depth is xk plus 1. Yeah. So this is the distribution of x of k plus 1. X of k plus 1 is xk with probability k over k plus 1, and it's 1 plus xk with probability 1 over k plus 1. Or to put it another way, xk plus 1 has the same distribution as xk plus a Bernoulli random variable, that's this extra 1. So it's 1 with probability 1 over k plus 1. Okay, maybe I'll wait here a bit.
And so we already forgot about n. We don't.
We forgot about n, so we'll keep growing until we reach n, but we are now looking at the tree which has been formed after adding k nodes. And it doesn't depend on n because the new node, okay, we've forgotten about time. We are now looking at the discrete time steps when an extra node is added.
Well, honestly, I don't understand why it's k over k plus 1 probabilities. So we have at the moment xk, yeah.
So xk, so we have a tree t sub k, and then if you pick a node uniformly at random in this tree, it has depth x sub k. So x sub k is the random variable, which is the depth of a random node from this random tree. So there are 2 levels of randomness. The tree itself was grown randomly, and then you uniformly pick a vertex from within that and look at its depth.
Yeah, this I understand, but I don't understand why the depth will not increase with probability k over k plus 1, but it's maybe my problem. No.
So you go from tk to t of k plus 1. So you have added only one more vertex.
Okay.
And now you are uniformly picking from one of these k plus 1 vertices. So maybe let's go back to this picture. Now you're uniformly picking from the blue and the red vertex. So here k is 1, 2, 3, 4. So k is 7, k plus 1 is 8. So with probability 7/8, the vertex you pick is blue.
Okay.
And it has the same depth as it had in the tree TK.
Mm-hmm.
So that is XK.
Yes, but then it's also will have the same depth, no?
Yeah, it has the same depth. So with probability 7/8, with probability K over K plus 1, it has the same depth XK.
Uh-huh.
But with probability 1/8, you pick this red vertex.
And I see that the depth will be also 2, no? I'm wrong?
Yeah, but we are not looking at the total depth of the tree. We are looking at the depth of just this vertex.
Ah.
Okay, so this vertex is at depth 2, but this vertex is at depth 1.
Okay, I got.
Yeah, so not the depth of the tree, but the depth of one vertex chosen uniformly at random in the tree.
Oh, okay, yeah, thanks.
Okay, and the depth of the tree itself will be the max of the X case. We'll come to that later.
Ganesh, may I comment? Again, so you also use, you didn't pronounce the fact that if you have uniform distribution on a discrete set, then if you take a subset of the discrete set,
yeah,
then condition on that subset, you again have a uniform distribution.
Yeah,
that's what you use in the line with probability k plus 1, this one.
Yeah, exactly.
Condition is uniform is again uniform.
Yes. I'm using that. Yeah.
Okay, thanks.
Okay, so this is the recursion for the distributional recursion for these random variables. And so this is a very easy recursion. So xn is just distributed as the sum of these independent Bernoullis with different parameters, 1 over k plus 1. And so its mean is asymptotic to log n. And then, okay, so that's the depth of a randomly chosen vertex. If you want the depth of the tree, you should look at the maximum of these, but you can show that these have rapidly decaying tails. So the maximum also is just some other multiple of log n. I haven't done that calculation, but the maximum will also, I think it's even in fact the same multiple. It also concentrates around log n. Okay. Okay, I'll have to think about that. Maybe it's a different constant, maybe it's the same constant, but it's still logarithmic in n. So the depth of the tree and the depth of a random vertex in it both scale logarithmically in n. Okay, so that completes the discussion of Rumour spread or first passage percolation on the complete graph. So we look both at the time for the Rumour to spread and the number of steps the Rumour takes to spread. And now we'll move on to general graphs, not just the complete graph. And here we'll be able to, so in the complete graph, we were able to give very refined statements, both about the distributional convergence of this time, fluctuations, large deviations, everything could be described very well. In general, we will be able to say much less. We are just going to give an upper bound of the Rumour spreading time. Okay, so we look at an arbitrary directed graph on n vertices, and the model for Rumour spreading is very similar. So we start with a single node which knows the Rumour. And now I'll directly go to putting the clocks on the edges rather than vertices. So we are going to put independent Poisson processes on each of the edges of this directed graph G. And okay, the symmetry in the original graph has gone. So all these edges could have different rates, lambda sub VW on edge VW. So this is the rate of the Poisson process on this edge. And capital lambda is the matrix consisting of all these n by n matrix consisting of these rates. And then these Poisson clocks determine when node V communicates to node W. And if V already knows the Rumour at this communication time, then it passes on the Rumour to W. Okay, so that's the model. Very similar to the complete graph model, except that there's no such symmetry, so we also allow the rates to be different. And we are interested in the same question of how long it takes until all n nodes know the Rumour.
So we can think that we still have a complete graph, but some lambdas may be 0.
Yeah. Thank you. Yes, that's correct. Okay, so the bounds are going to depend on some quantity which we'll call the conductance. And we'll use this to prove an upper bound of the Rumour spreading time. So this is just the definition. We'll denote the conductance by capital phi, so phi of lambda. So we look at the minimum of all subsets of the vertex set, all subsets which are neither empty nor the whole thing. And then we look at this ratio. So on the numerator is the number. So for every edge going from S to S complement, you look at the intensity of the Poisson process and you add it up over all edges crossing this cut from S to S complement. And the denominator depends on the sizes of the sets S and S complement, and we just put in the 1 over n renormalization. So it's similar to expansion parameters of graphs, but now it's a weighted graph with these weights, the rates of communication. So you look at the total rate of communication from S to S complement and rescale it by something that depends on the product of the sizes of these sets. Okay.
So phi what phi of lambda equals to what if all lambdas are 1?
We are going to calculate that in a moment. We'll do some examples. We'll do it for 1 over n, but okay, it's the same as 1, but up to scaling. Yeah. We'll first do some examples to calculate this conductance, and then we'll prove this theorem, which is the upper bound on the Rumour spreading time. So it's the same 2 log n as for the complete graph, but now divided by the conductance of your graph. And this bound holds for any initial node knowing the Rumour. Okay, so the example of the complete graph, if you recall the complete graph model we described, there's rate 1 over n of communicating on each edge. So the matrix lambda is the matrix with all elements equal to 1 over n. Okay, so this is very similar to Sergei's question, where he wanted 1 everywhere here. Okay, so let's take a subset, arbitrary subset S consisting of k nodes. Then what can we say about the sum? Lambda VW is 1 over n for each V and W. But the number of such terms in the sum is k times n minus k, because there are k nodes in S and n minus k in S complement, and there's an edge between every pair of them. So this is the ratio we get, and 1 over n times size of S complement is exactly the same thing. So the conductance is the minimum over all subsets of the ratio. The ratio is 1, the minimum of 1 is 1. So the conductance is 1 for the complete graph. And then the theorem tells us that the Rumour spreading time is 2 log n divided by conductance. So the bound we get is 2 log n. And in this case, the bound is tight. Okay. So our theorem gives us a tight bound for the Rumour spreading time on the complete graph. And let's do a couple more examples. So the next example we are going to look at is a cycle graph. So we have n nodes arranged on the circle, and each node is just connected to its 2 neighbors. And I'm going to assume that each node communicates at a total rate of 1, just like in the complete graph. So it's going to, there'll be rate half to each of its neighbors. So that's the model we'll look at. So I say that in words here. So Cn is the cycle graph, and lambda VW is a half for each of your neighbors. So on each edge, in each direction, each edge is bidirectional. The rates are all a half. And again, let's pick a subset S with size k, and then look at the sum of lambda VW, where V is in the set and W is in S complement. And I claim that the sum is at least 1, and you have equality if the nodes are all next to each other. So let's go back to the picture. So if I pick these 4 nodes next to each other, if that's my S complement is the remaining node. So it's only the 2 edges at the boundary along which which go from S to S complement. So the rate is the sum of these 2 rates on this edge and this edge. So it's a half and a half, so it adds up to 1. But if my 4 nodes were separated, so maybe if I took these 2 nodes here and those 2 nodes there, then there would be 4 edges going from S to S complement, and the sum would be bigger than 1. Okay. So the sum depends on which particular subset you pick, but it's always at least 1, and it's exactly equal to 1 if you pick the k nodes all next to each other. Okay. And then the denominator, 1 over n size of S complement, is just this. So the conductance is the minimum over all subsets of 1 divided by that, which I've written. So the n goes into the numerator. So it's the minimum of this ratio over all k between 1 and n minus 1. And it's clear that to minimize this, you want to maximize the denominator. So you want to take k to be n over 2 if n is even, or close to n over 2 if n is odd. And then you get 4 over n roughly for large n. Okay. Okay, so the conductance for the cycle graph is 4 over n. And if you use the theorem, this says that the Rumour spreading time here is no longer bounded by log n, but it's bounded by n log n over 2. So this is what you get. You can also calculate exactly, because this graph is so nice and symmetric, exactly what the expected Rumour spreading time is, and it turns out to be n minus 1. So the bound is not so bad compared to n, but it's not tight. It's the bound is a factor log n bigger than the true value, a multiple log n of the true value approximately. Okay, so that's what you get on the cycle graph. You can do similar things on the star graph. So the star graph on n nodes, there's a hub and there are n minus 1 leaves. Each leaf is only connected to the hub and nothing else. And again, we'll assume that each node communicates at rate 1. So the leaf always communicates to the hub. So at rate 1, it talks to the hub. The hub has equal chance of talking to any leaf, so it communicates at rate 1 over n minus 1 to each leaf. So that's what we have. So lambda VW is 1 if it's the leaf talking to the hub, and 1 over n minus 1 if it's the hub talking to the leaf. And again, for a given subset of the vertices of size k, we can calculate the sum. So if S contains the hub, if the subset contains the hub, then there are another k minus 1 leaves which are in the set. I should have made some more colors in this picture. Okay, so suppose S consists of the hub and maybe these 2 vertices. So S is these 3 vertices. S complement is these 4 leaves. So there are these 4 edges going from S to S complement, and the rate on each of these edges is 1 over n minus 1. So it's n minus k. I should have put n minus 1. This n is a mistake. It's n minus 1 here, but okay. So they are closed for large n. So this is the ratio if S contains the hub. If S does not contain the hub, you are counting things from the leaves to the hub. So the rate is 1 and there are k leaves, so it's k. But that's fairly easy. And then you do the minimization and it turns out that the minimum, I think it should be 1 over n minus 1 because of my mistake, but that's what you get. Okay. Okay. So, so the conductance in this case is 1 over n. So again, the implied bound is on the mean Rumour spreading time is 2n log n, but the actual value is about n log n. So irrespective of where you start, if you start at the leaf, it only takes one time step to get to the hub, but the hub to the other leaves takes most of the time. Okay, because you are only talking at rate 1 and you have to communicate the Rumour to n leaves. So you typically take unit time to find a new leaf, and this extra log n comes from the coupon collector problem. So if you remember the coupon collector problem, you are at each time you get one coupon from a set, a uniformly chosen coupon from a set of n coupons. And how many coupons do you need to collect before you collect all n? You need n log n coupons, and that's what is giving you this n log n time for the exact value. Okay, so again, it's not tight, but the error is only a factor of 2 in this case. So these are some examples.
Ganesh, sorry, we have a question from chat. Mikhail asks, what will happen for a graph in which each vertex has exactly k neighbors for some k?
Okay, so you want to have a regular graph. It's up to you how you specify the lambdas, but let's say you specify the lambdas to be equal, so 1 over k. But this will depend very much on the graph itself. So if you look at, okay, so let's take k equals 4. So you have 4 neighbors. And here are 2 very different graphs. So you take the 2-dimensional lattice and then just turn it into a torus to get rid of boundary effects. That graph has very low conductance. The lattice, like the cycle, has low conductance. So for the cycle, the conductance was a constant over n, and for the lattice, again, I don't know if it's 1 over n or 1 over square root n, something like that, but it's pretty small. It's going to 0. But if instead you made it a 4 regular random graph, that's an expander. That's a graph which locally looks like a tree. And in that case, the conductance will be a constant. It won't vanish like 1 over n. Okay, so the degree alone doesn't determine the conductance. The conductance depends on the large scale structure of the graph.
Okay, thank you.
Okay. Okay, so let's go back to the theorem of the upper bound on the Rumour spreading time, and let's give a proof of that. The proof is going to be quite similar to that for the complete graph, so we've done most of the hard work. So again, let's define T sub k to be the first time that k nodes know the Rumour, and initially a single node knows the Rumour, so T1 is 0. So in the complete graph, there was a lot of symmetry. So we only needed to keep track of how many nodes knew the Rumour, and that would determine what would happen afterwards. In a general graph, that's not true. It depends very much who knows the Rumour. If there may be one densely connected subset where if somebody knows the Rumour, it's different from if somebody knows it in some sparsely connected subset elsewhere. So we have to keep track of who exactly knows the Rumour. And so we are going to do this with the set S sub t, which tells you who knows the Rumour at time t. And so S sub k is going to be s at time tk. So these are the k nodes that know the Rumour at time tk. And we need to keep track of this. Okay, so now we are going to condition on sk. So we'll again look at, so in order to analyze the Rumour spreading time, we are going to look at tk plus 1 minus tk, how much longer it takes starting from tk until one more node learns the Rumour. But to calculate this time, we need to condition on sk. Who are these k nodes that know the Rumour? Okay, and given sk, the total rate at which you get communications from informed nodes, V in sk, to uninformed nodes, W in sk complement, is just the sum of rates lambda VW on all these edges. Again, because of the model which says that the communications, there are Poisson clocks at these edges, and the communication happens when one of these Poisson clocks rings, and the superposition of all these Poisson processes is Poisson with this total rate. So this is the rate at which the Rumour spreads from sk to sk complement. Okay, so the time conditional on sk is exponentially distributed with this parameter. So the mean time for one more node to learn the Rumour is 1 over this total rate. Okay, so that's the bound. And then by the definition of the conductance, so the conductance was defined as the sum divided by 1 over n sk s complement minimized over all sets. So for any particular set sk, the sum is bounded below by the conductance times this. Sk by definition is of size k, so it's the conductance times this ratio. And so no matter what the set sk is, the conditional mean of tk plus 1 minus tk is bounded by this quantity, again expanding in partial fractions, 1 over the conductance times this. And then the rest of the proof is the same. So we write Tn as the telescoping sum of tk plus 1 minus tk by linearity of expectation. It's the sum of these expectations. And then the expectation is the expectation of the conditional expectation given this set. But no matter what the set was, we have this bound on the conditional expectation, and we add this up and we get 2 log n over the conductance. Okay. Okay, so that's the bound, and the proof is quite easy. It's the same as before. And then, so let's discuss some things about this bound. So natural question to ask is this upper bound good in general, or can it be very loose? And in the examples we saw, it was tight on the complete graph. It was pretty close on the star. It was off by a factor of 2. Bit worse on the cycle, off by a factor of log n. But okay, is there a worst, or can it be arbitrarily bad? And as far as I'm aware, it can be arbitrarily bad. There are no, I can't say that for all graphs, the worst that can happen is log n. It could be even worse than that. So the upper bound in general is not tight, but it does tend to be good on expander graphs. So an expander is a graph in which the conductance is bounded below by some constant which doesn't depend on n. So if you think of a sequence of such graphs, n going to infinity, then the conductance remains bounded away from 0. Whereas in the cycle or the star, it went to 0, like 1 over n. Okay. So in those graphs, the upper bound is saying that it takes some multiple of log n for the Rumour to spread, but there's also a lower bound. It can't spread on, generally speaking, faster than log n, though there are some exceptions to that. But so on expanders, the bound tends to be good. But on other graphs like the cycle or on lattices, it can be quite poor, and you can, there's this dumbbell graph which consists of two cliques joined by a long thin line of nodes, and that has very poor conductance, and there the bound can be very bad. Okay, so it's not a universally good thing, but in some examples it works well. Okay, so my other comments are mainly about applications, etc. So yeah, as I mentioned earlier as well, many distributed algorithms rely on spreading information throughout a network in order to do some maybe distributed computation. So rumor spreading is used by them, and that's why we are interested in understanding how quickly rumor spreading happens in general graphs, because that tells you how quickly these algorithms converge. There was a question, I think again from Sergey very early on, about what happens if you, or was this from Evgeny? Anyway, there was a question about what happens if you have multiple rumors, not just one. And yeah, so this has been proposed as a model for algorithms like BitTorrent. So BitTorrent is an algorithm for disseminating files on the internet, and the file is broken up into chunks, and so each of the chunks spreads more or less like a rumor. And so you want to ask how quickly do those spread, and that has been studied as well. I'll provide a reference for that. So that's also a model of interest. Okay, and so far all the graphs we have looked at are static, but you can also ask questions about how quickly do rumors spread if the graph is either growing, or if it's the number of vertices is fixed, but the edges are changing over time. And maybe there's even an adversary changing the edges. So an adversary may pick which edge to keep at every time step, potentially even knowing which nodes are already informed. They may selectively choose which edges to keep and which edges to remove. And in such cases, can you give bounds on the rumor spreading time? So that's been studied. Okay, so one thing I should mention, though it's maybe obvious, but clearly a rumor can spread to every node on a general graph. In order for it even to be possible, the graph should be connected, and in fact strongly connected, meaning there's a directed path to every vertex from the source at least. And so implicitly the conductance takes that into account. If your graph were disconnected, the conductance would be 0, and so the upper bound would be infinity, and so that the upper bound still works in that case. And so if you're thinking of adversaries, you have to limit the adversary. The adversary shouldn't be allowed to disconnect the graph or to prevent you talking to the complement of the subset. But the conductance takes that into account. And so if you can impose some condition on the minimum conductance the adversary can achieve, then these bounds typically carry over to the adversarial setting. And there's I'll point out the reference on that. And then there's another set of problems that has attracted some interest, is that of identifying the source of the rumor. So this is quite different from the topic of this lecture. It's a somewhat independent topic, but since it's an interesting problem, I thought I'd mention it. So you have a rumor starting at time 0 from a single vertex. It spreads for some time. So as we saw, okay, so it spreads for some time on a general network. And so you see, you get a subset of nodes that know the rumor. So you take a snapshot at some time, you know just the subset, and you want to know who started the rumor based on just knowing the subset of which nodes know the rumor. And you also know the whole network structure. So you know which are the edges between these, so you also know which are the edges to the remaining nodes which didn't hear the rumor, etc. Given all this information, can you identify the source? And there's been some nice work on this. It turns out that if the rumor is spreading on trees, on regular trees or Galton-Watson trees, then you can in fact identify. So you should think of the network as being very big and the rumor having spread for a fairly long time. So the network has 1 million nodes and 1,000 nodes have heard the rumor. Can you identify the source? And it turns out that if the network is a tree, you can exactly identify the source with probability bounded away from 0. Okay, that's quite a surprising result indeed. No matter it's spread to 1,000 nodes, but you can find the exact source with the probability may be small, maybe 0.1, but it's not going to 0. It's bounded away from 0 no matter how long the rumor has been spreading. But this is on trees, regular trees or Galton-Watson trees. On networks, I don't know of similar results, but at least on simulations, there's evidence that some of these algorithms do well. So that's another class of interesting problems. So I'll end with some references. So the first paper here I think this was one of the seminal papers which is using gossip or rumor spreading to do distributed function computation. So let's say you want to calculate the mean of some. So there's a value at each node. Maybe it's a sensor network measuring temperatures, and you want to calculate the average temperature from these sensors or the sum of the temperatures or something. So this algorithm tells you, this paper presents an algorithm which relies on rumor spreading to do this computation. And so the bound on the rumor spreading time gives you a bound on the time for the algorithm to converge. And the presentation that I made is adapted from the results in this paper. So the analysis of BitTorrent that I mentioned, so with multiple rumors, that's by Sanghavi, Bruce Hayek, and Laurent Massoulier. This is a very nice paper as well. The rumor spreading, so identifying the source of the rumor, that was again very seminal work by Devraj Shah and Tawhid Zaman. So I recommend this paper as well. Then the adversarial setting for rumor spreading was studied by these people. And I also wanted to mention a recent paper of mine where we used rumor spreading for multi-agent bandits. So this is by no means comprehensive. Rumor spreading is used in lots of distributed algorithms. So these are some example references. But this is maybe the key starting point of a lot of this body of work. Okay, that's all I wanted to say today. So I'll answer questions if there are any, and if not, stop sharing the screen.
Okay, thank you, Ganesh, for this lecture very much. So now we will make this administration organization moment. I think we can stop sharing, yeah, now. And we ask you, all the participants of this school, to turn on your video. Of course, if you can, yeah? It's not like mandatory, you have to, and so on and so on. And we do this to say thanks to Ganesh for the lecture. So there is like the way to press the button for applause. I will applause by myself. Thank you very much for the lecture. And now we can ask questions about everything of this. So anyone who has questions, maybe some comments, something like this, everything, you're welcome. I have, okay, Sergey. So,
I may ask, so the question is, so assume in addition that everybody has a memory, and memory is not infinity. So yes, at some point I remember, at some time I remember something, somebody said something about it, but then I forgot. So essentially, you might think the simplest setup it's also exponential. So one can, so then to some extent the distribution of Rumour is stabilizes in time.
Yeah.
What and how does the size of this guys who keep the Rumour? So how does it behave? How does it look like? It's whatever and so on and so on.
So this model that you propose is exactly the epidemic model, which we'll look at later. So you get infected with the rumor, and after some time you forget, so you recover from being from the infection. So and then you can become infected again if you hear it.
So there is a two-state process, no immunization.
No immunization, yeah. So you just recover spontaneously, you forget the rumor, and then you can become reinfected. You gain no immunity. You can relearn the rumor. And then, so two things can happen. So the rumor can keep being refreshed indefinitely, or after some time, everybody forgets, and then the whole system, nobody knows the rumor anymore. In a finite network, eventually that will happen, but there's a kind of phase transition. It can happen quickly, or it can happen very slowly, depending on how soon people forget.
Thank you.
Okay, so now you start to talk in the word infected, but nowadays everybody is talking about virus in all countries and so on. So can we change the word rumor on virus and talk about COVID on all this situation? How it's maybe not good, but anyway, can we?
So maybe I didn't fully understand your question. So what would you like to? So I'm using rumor for the model where you don't forget, and infection for the model where you do forget. But other than that, they are quite similar. Forgetting and recovering are quite similar. Okay, there are two kinds of infection models, the so-called SIS epidemic, where you don't get immunity when you recover, and the SIR model, where you have immunity after you recover. And there are somewhat different questions of interest in both these models.
Okay, yeah, I got. In SIS, you also can model it with differential equation. Am I right?
Yeah, so if it's SIS on a complete graph, then you can model it in the large population limit with a differential equation. So that's your law of large numbers limit or hydrodynamic limit of the.
Okay, thanks. So, anyone else? Questions, comments? I have administration question. You can think about all the others. Ganesh, could you send us slides that we will resend them to all the participants? And also, I think today we will have a link on YouTube for this lecture, so everyone can look on it again. And if someone missed something, then you can remind yourself what was here. So, what about more questions? Any comments? Everything is very good. Everyone understand everything? Yeah, Marina said yes, Anastasia as well. Alexandra is smiling. Okay, cool. So thanks again, Ganesh, for your lecture.
Thank you.
The next lecture will be in 2 weeks. Am I right?
Yeah.
So we will have a seminar, maybe not even one. So we will have maybe 2 seminars, maybe even more. We'll see how it will go. But the next lecture will be in 2 weeks, and it will be 22.
Yeah,
okay.
22. Okay.
Thanks, Ganesh, again. Thanks
Thank you.
everybody for coming here, for listening us. Not us, but anyway. So see you next time. Bye-bye.
Bye.
Thank you. Bye.
Thank you. Bye.
Goodbye.
Bye.